All right, in section 9.2, we're going to be dealing with the rules that are related to probability. So here we're going to be talking about the probability of event A or B when you're dealing with mutually exclusive events, and also for any events A or B, whether it's mutually exclusive or not. And then we'll look at independent events and the probability of event A and B and their formulas that are related to it. Also, conditional probability. And also we'll look at a tree diagram, how to use a tree diagram to represent and analyze probability problems. Okay. So let's start with we'll start with determining the probability of event A or B when we're dealing with mutually exclusive events. Okay. So here the event A or B is one event consisting of what they call the union of the outcomes in events A and B. And the word or is going to be that inclusive or, meaning either event A or event B, or it could be both events A and B. Okay. So in this example here, let's say I want to list all the outcomes that belong to event A or B. So in part A, I got event A with the elements 1 and 3, and B with the elements 4 and 6. Okay. So what that means there is this. A is the event of getting a 1 or a 3, and B is the event of getting a 4 or a 6. So in this case here, the event A or B is just the event of getting a 1, a 3, a 4, or a 6. So we're just combining the two together. That's what or means. Actually, it's the union of the two. So we're just uniting the two, just joining the two together. So A or B would be 1, 3, 4, or 6. And that's the event of getting a 1, a 3, a 4, or 6. Okay. And in part B, you want all the outcomes that belong to the event A or B. Now, A, of course, is going to be the event of getting a 1 or a 3. B is the event of getting a 3 or a 6. Now, if we put the two together, notice we don't repeat the 3. Okay, so event A or B is just the event of getting just a 1 or 3 or 6. Okay, and that's the set right there for that event, A or B. And in fact, parts A and B in that example represent the definition of what is mutually exclusive and what is not mutually exclusive. So in part A, that fits the definition of mutually exclusive events. In other words, A and B are mutually exclusive events when A and B cannot possibly occur at the same time. In other words, they don't have any common outcomes. So if I go back to part A in this case, pretty much you can see that A and B have no elements in common. However, in part B, you'll see that there is one element in common. That's the number 3. So in part A, that would be considered mutually exclusive. And in part B, it's not mutually exclusive. Okay. And now, if we know that event A and event B are mutually exclusive, then we could find the probability of event A or B in terms of the probability of event A and the probability of event B. So here's another definition. Okay. A and B are mutually exclusive events, meaning though they have nothing in common. That means that the probability of A or the probability of B would be the sum of the two probabilities. The probability of event A plus the probability of event B. All right, now let's look at this example that deals with mutually exclusive events, where the following data are based on a report by the CDC from the National Hospital Ambulatory Medical Care Survey for outpatient department visits. Here's that table at the bottom. And we want to know, what is the likelihood that a patient visited the outpatient department because of an acute problem or for preventative care? And interpret the result of part A. Okay, so that's what the table looks like. Now I can see here that these events are mutually exclusive, okay? An acute problem and preventative care have nothing in common. Okay. So those are mutually exclusive events. Okay. Now on the next slide, we're letting A represent the event that the patient visited the outpatient department because of an acute problem. B would be for preventative care. And those are mutually exclusive because the visits are for acute problems are unexpected emergencies. Preventative care are scheduled. So we just simply add the two probabilities together. The probability for the person visiting for an acute problem was 0.36, and for preventative care, that probability was 0.18. So we just add the two probabilities together, you'll get 0.54. So that represents the probability of a patient visiting because of an acute problem or for preventative care. Okay. And on the next slide, part B, now they have 54%, they just changed the decimal to a percent. And what that means is 54 out of 100 patients visiting the outcare department would be seen either for an acute problem or for preventative care. That's just the interpretation of that. Okay. Questions on that example? Okay. Now let's look at problem number 1, where we have events A, which is 1, 2, and 6. And event B, which is 3 and 5. And of course, our sample space is just simply 1 through 6. Now those numbers. Now they say make a Venn diagram for these sets, and then explain how the Venn diagram for events A and B would reveal A and B are mutually exclusive events. Okay. So this is what we have here. Now, the Venn diagram, I don't know if you're familiar with a Venn diagram. It looks like this. Has a rectangle, and there are circles that are inside that rectangle. They could be either joining together or not. But in this case, if I look at A and B, there's nothing in common. There's no number that's in both. So these circles do not join together. I'm gonna let this circle be event A, this circle be event B. And then we just fill in the numbers for A and for B. Event A has the elements 1, 2, and 6. And then event B has just the numbers 3 and 5. Now the sample space is just going to be this whole Venn diagram. Now we do have the 1, 2, 3, 5, and 6, but we're missing the number 4. So the number 4 would go somewhere in this rectangle, but it won't be in either of those two circles. So that is what the complete Venn diagram looks like. Okay. So that's part A. Now, part B does say, explain how the Venn diagram for events A and B would reveal that A and B are mutually exclusive. Well, if it's mutually exclusive, that means these two events have nothing in common. So by looking at this, we can just say that the Venn diagram shows that A and B have nothing in common. Right? Any questions about problem number 1? Because all they're doing is just asking you for a Venn diagram created from that, from what's given to you for A and B and the sample space, and then interpret it what that means to show that A and B are mutually exclusive events. Okay. All right, now this is problem number 5, parts A and B. Okay. Now there's more to this when we get to, as we go along in these slides here. Here we got a Venn diagram that represents events A and B for a sample space S with equally likely outcomes. Okay. And I think we kind of talked about what equal, I don't know if we talked about equally likely outcomes are, but what that means is this, that each element or each element, I would say, has an equal chance of being selected.
Like paradise, right?
Yeah. Mm-hmm. So that has equally likely outcomes, or tossing a fair coin. So what I'm gonna do is copy over that Venn diagram that we have. And notice that these circles in this case are connecting each other. This is the sample space. This is A. This circle is A. The other circle is B. And there are 3 dots here. Keep that on that side. Now, in that problem, they ask for what is the probability that event A will occur? And part B, what is the probability that event B will occur? Okay. So let's look at this. So here's event A right here. How many dots are there in this circle for A? There's 6. And then I need the total number of dots that are in this Venn diagram, which is 15. So the probability that event A will occur would be 6 out of 15. And if we were to reduce that in simplest form, that would be 2 over 5. And I'm also going to ask for this. I don't know if the homework would ask for it, but 2/5 as a percent. If we do 2 divided by 5, multiply that by 100, what will we get? 40%. So that probability will be 2/5 or 40%. Okay. And now part B is the probability that event B will occur. Well, here's the circle for part B, for event B. How many dots are there in that circle? There are 10 out of the total of course, 15. So that'd be 10 over 15 if we were to reduce that in how much, 2/3? And then 2/3 as a percent, I'm gonna say 66.7% approximately. Okay. So that's the probability that event B will occur. All right, any questions on this? All right, on the next slide, we'll talk about how to determine the probability of event A or B. And this will be for any events, whether they're mutually exclusive or not. All right, let's take a look at this situation. Let's say an experiment consists of rolling a standard die and then recording the number of dots that appear on the top face. So here we got event A means that we can roll a 2 or a 4. And then event B, we roll either a 2 or 3 or a 5. And I want the probability of event A or B. Okay. Now notice, this is a situation where these 2 events, A and B, are not mutually exclusive, because if you notice, the number 2 appears in both events A and B. So we're not going to be able to do the addition rule on this one. The probability of event A plus the probability of event B. All right, now we have the sample size of 1, 2, 3, 4, 5, and 6. We have that. The probability of rolling it of event A would be, of course, 2, 6. Because if you look at event A, a 2 and a 4, those are 2 possibilities out of a die that has 6 faces. And probability of event B, that's 3 out of 6. There's only 3 numbers out of all 6 on the fair die. Now on the next slide, A or B would be 4 over 6. Okay, because that's a 2, a 3, 4, and a 5. That would be 4 over 6. But for A and B, we have to consider the 2, because 2 is in both A and B. And the probability for that would be 1 over 6. So to find that probability is going to be this. A or B would be 4 over 6. Or, in this case, 5 over 6 minus 1 over 6. Now, for A, it's 2 6 plus 3 6 minus 1 6. I think they're working backwards on this in this case to get you what that formula is for A or B when you do not have mutually exclusive events. And this is it. Probability of event A plus the probability of event B minus the probability for A and B, where it occurs. Because here the probability of event A was 3 6. For B, it was 2 6.
Professor, does this only work for 2 possible outcomes? Or can it work for 3 or 4?
Just, I think just for 2. Because I haven't seen one for 3 or 4. Okay, let me go back to this. And I might need to explain this going this way. So that probability of event A, if I go back to it, that was 2 over 6. And the probability of event B was 3 over 6. Now, what was common in both? Yeah, the 2. And that probability was 1 out of 6. Okay. So that's 2 6 plus the 3 6 plus the 1 6. Two 6 plus 3 6, that's 5 6. 5 6 minus 1 6 will give you 4 over 6. So the probability of getting an A, this should be 4. Apologize for that. So A or B, that probability ended up being 4 over 6. Okay. And of course, that's the definition for the probability of A or B when you do not have mutually exclusive events. So you have to use that, the probability of A plus the probability of B minus the probability of A and B. So let's say in this example, We have an experiment consisting of drawing a card from a standard deck of cards. What is the probability of drawing a spade or an ace? All right, so here we got two events. One is drawing a spade, the other one is drawing an ace. Now, what belongs to both events? There's a card that's the ace of spade, because you do have an ace and then there is a spade, because in a deck of cards there are four suits: spades, clubs, hearts, and diamonds. And of course, there are 13, there are four aces. And you do have the ace of spade in there. So it belongs to both events. So that's why it's not mutually exclusive. All right, so if we want the probability of drawing a spade, that would be 13 out of 52. Because there are 13 spades in a deck, from ace of spades to the king of spades. And there are four aces: ace of spades, ace of hearts, ace of clubs, and ace of diamonds. So the probability of drawing an ace would be 4 out of 52. Okay. And there is one card that has both the spade and the ace, which is the ace of spades. And that probability will be 1 out of 52. Okay, so we had to use the other formula where you have to do the probability of A plus the probability of B minus the probability of A and B. So the probability of space 13 over 52 plus the probability of getting an ace 4 over 52 minus the ace of spades, 1 out of 52. That will end up being 16 over 52, or approximately 30.8%. Questions on that? All right, suppose we have this problem number 2. And here we're just dealing with events A and B and the sample space. And this could be something like rolling a fair die. So the sample space will be all 6 numbers on that die. And the event A would be rolling a 1, a 2, or a 6. Event B would be rolling a 2, a 3, or a 6. And the sample space is that. Now let's say we want to make a Venn diagram of those two sets. So I'm going to write this down. Event A has 1, 2, and 6. B has 2, 3, and 6. Our sample space is 1 through 6. So my Venn diagram will look something like this. What's in common in A and B? The 2. And what else? 6. So here I got 2 numbers that are in common. So my circles will be intersecting like this. So this will be A, that's B, and I'm going to say S is sample space. So what goes inside these two intersecting circles would be the 2 and the 6. The 1 will be on the outside for A, and B, only the 3 will be on the outside. Okay? And I'm missing a couple of numbers here. 4 and 5. So I'll put the 4 and the 5 out here. So it's going to look like this. That's the Venn diagram. And in part B, they ask you to explain how the Venn diagram for events A and B would reveal that A and B are not mutually exclusive. Well, here's the Venn diagram. Reveals that the intersection is non-empty. Is there something in common in both A and B? Questions on that? Okay, so if I did want to find the probability of A or B from this, then I have to use this, the probability of event A plus the probability of event B minus A and B occurring. It's probability. Okay, so the probability of event A, if you look at event A, in this circle, there are 3 numbers out of 6, plus the probability of event B, that's this circle right here, 3 numbers out of 6. But here we got to subtract out the intersection of A and B. Here there are 2 numbers that are intersecting out of 6. So this would be 3, 6 plus 6, 3, 6 plus 3, 6 minus 2, 6. That's going to be 4 over 6. Questions on that?
Did you want to reduce that even?
Yeah, to 2/3. If they ask, or as a percent, approximately 66.7%. Okay. All right, any other questions? Okay. All right, now let's look at this particular problem, number 5. This is only part D. Okay. So here we got the same Venn diagram, and it represents A and B for a sample space S with equally likely outcomes. And here I want to find out what is the probability that event A or B will occur. So here we got the intersection of the 2. Okay. Okay. So the probability of A or B, since we have something in common in A and B, we have to use the probability of A or B equaling to the probability that A occurs plus the probability that B occurs, and then we have to subtract its intersection of A and B for that probability. So, and I think we already talked about this was 15 dots, so that means the probability of event A was 6 out of 15. The probability that event B occurred, that was 10 out of 15, yeah. Now, how many dots are in the intersection? 3 is the intersection right here, the 3 dots. That's the probability of event A and B. So what's 6 15ths plus 10 15ths minus 3 15ths?
86%.
Yeah,
You want us to multiply by 100?
yeah. If the homework asks for a percent, then they're gonna want you to do that.
Okay.
All right, any other questions? And this is, of course, problem number 5. Okay. Let's look at events A and B for independent events. Independent events. All right, now, what do we mean by independent events and what do we mean by dependent events? When we say 2 events, A and B, are independent, we're meaning that the occurrence of A does not affect the probability that event B will occur. Example of that would be tossing a fair coin and rolling a fair die. Those can be considered independent, okay? Because what I get on the fair die would not depend upon what I get on the fair coin. Okay. Now, of course, dependent means what I get on for event A has an effect on the probability that event B will occur. Okay, so we're going to talk about that, what dependent means, in a few minutes. So here's an example. Determine the probability of drawing an ace from a standard deck of cards. And then part B, an experiment consisting of drawing 2 cards from a standard deck of cards with replacement, meaning that we return the first card to the deck before drawing the second card. Okay. Now let's say here A is the event that the first card is a 5, and B is the event that the second card is an ace. So why would event A and event B be independent? Okay.
Because it's 1 out of 52, right?
Well, okay, let me jump to the answer in part A, where it says here, determine the probability of drawing an ace from a standard deck of cards. Well, there's only 4 aces out of 52 cards in a deck, so the probability would be 4 out of 52. Now the part B, where the experiment consists of drawing 2 cards from a standard deck of cards with replacement. Okay. Let's assume that event A occurred when a 5 is drawn and then returned to the deck. There are 4 aces in the deck of 52 cards, so that probability of drawing an ace is still 4 out of 52. And in this case, that occurrence of us drawing an ace didn't affect, drawing a 5 didn't affect the probability of drawing an ace. So it's still going to be 4 out of 52. So event A and event B are independent. So usually something with replacement, meaning you put the card back in the, you draw a card on the first time, you put it back in the deck, and then draw another card. That's considered to be independent. Okay. Now for something that's dependent, it'd be something like this, without replacement. That means on the first draw, whatever you draw out of that deck, you don't put that card back in. That means you're going to have 51 cards remaining to draw. Okay? So in this case, you assume that event A occurred, where a 5 was drawn and not returned to the deck. So now you got 4 aces in a deck of 51 cards remaining. Okay, and then we go back to that side because that does talk about without replacement, which is this right here. Meaning we don't return the first card to the deck before we draw the second card. And with that, that means that the sample space has reduced from 52 to 51. So that's what that means by without replacement. Okay. So on the first draw, it was like 4 out of 52. Then now we don't replace the card back. So now it changes from 4 out of 51 on the second draw. So events A and B are considered to be dependent. So what we do on event A can depend upon the probability that event B will occur. Okay. All right. So if events A and B are considered to be independent, then the probability that both A and B will occur. So now we got the keyword and happening, whereas before we had or. But here we're dealing with and. So the probability of event A and B would be just multiplying the two probabilities. The probability of event A times the probability of event B. All right, now let's say we had an experiment consisting of tossing a fair coin 5 times in a row. Which outcome is more likely? This one where we have the heads, tails, heads, heads, and tails, or all 5 tails. Yeah. Now, here we're dealing with independent events. So what that means here is this. What we get on the first toss doesn't depend upon what we get on the second toss, or the third, or the fourth, or the fifth. Okay? So those are independent events. Now, when we're tossing a fair coin, the probability of getting a head is 1/2, and the probability of getting tails is 1/2. Okay? So all we do there is just multiply each one of those probabilities here, as you can see. And that's going to be 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is, of course, 1/32. And then for a probability of getting all 5 tails, we do the same thing, multiply each probability for getting a tail, or getting tails, which is also 1/2 times 1/2 times 1/2 times 1/2 times 1/2, and that's also 1/32 as well. So you're going to get the same probability here on both situations here. So they're equally likely. Question?
Yes, sir.
Go ahead.
Having a repeatable phenomenon like that, isn't there some rarity that occurs to it?
Not really. I mean, we're tossing a fair coin 5 times.
Then the more times you end up with the same result, the more unlikely it is. You don't toss a coin 50 times and always end up with nines.
Oh, you're talking about something else. I mean, tossing a fair coin 50 times. But here we're just dealing with independent events. I know what you're talking about here because you're talking about, I think, the law of large numbers where you have to, where, you know, the more times you toss a coin, like 50 times, you're just looking at the number. Let's just say you're looking at the number of heads after so many tosses. Let's say 500. You count how many heads you got. Okay, that's just the experimental probability that you're dealing with. Okay, that's another thing that we talked about earlier. All right, any other questions? Okay, now this is problem 5C. The probability that event A and B will occur. And that's for a sample space with equally likely outcomes. Until we get A and B, and I apologize I didn't give you an example of something like that we just got to be talking about. I will. All right, so A and B. How many dots are in A and B? The intersection.
For the intersection.
Yeah,
3.
the 3. And the total number of dots we established is 15, so that's 3 out of 15. If you reduce it, it'll be as a fraction 1/5, or actually, it's going to be exactly as a percent, 20%. So the probability that event A and B will occur will be 20%. All right. Questions on that particular problem? This is just part C of problem number 5. Okay. All right, here's problem number 12. You're given the probability that event A occurs is 0.3, and the probability that event B occurs is 0.5. A and B are independent events, and we want to compute each probability. So in this case, we want the probability of A and B. And we're given that the probability of event A is 0.3, the probability of event B is 0.5. So A and B, we have to use the formula where you have to multiply the 2 probabilities together. Probability of A times the probability of B. Right. So we just take 0.3 times 0.5. That'd be 0.15. Okay. Now, part B just say the probability of A or B. All right, for this case, let's assume that events A and B have something in common. Okay, let's say A and B have something in common. That means we have to use the other formula for computing this probability. And the word or is this. You have to use the word, you have to use a plus for that. Probability of A plus the probability of B. But let's say that there was something in common. You have to do this, minus the probability of A and B. All right, so the probability of event A was 0.3, plus the probability of event B would be 0.5, minus the probability of A and B. Well, we've already figured this one out in part A. Here, the probability of A and B came out to be 0.15. So what's 0.3 plus 0.5 minus 0.15? 0.65. All right. Any questions about problem number 12? Okay. So let's say we have something like this. This is problem number 13. And that should say page 523 in the textbook. Here we're given that probability of A is 0.42 and the probability of B is 0.75. A and B are independent events. So these are done the same way. Okay. So here's the probability of A and B. And with the word and, we use multiplication. We multiply the two probabilities, A and B. So the probability of event A is 0.42 times the probability of B is 0.75.
You get
0.315. Okay. Questions about part A? Okay. Now part B is the probability of A or B, and assuming that A and B have something in common. We have to use this formula here. So probability of event A is 0.42 plus the probability of B, that's 0.75, minus the probability of A and B, which we found out to be 0.315.
0.8.
Okay. 0.855. How much? Approximately 86%? Yeah. And I guess they want this as a decimal, depending upon what's in the homework, how they want their answers. Okay. Now, some of you might be thinking, why can't we just use the probability of event A plus the probability of event B? Well, if I added these two, I would get something like 1.17, which would not make sense because probabilities are numbers that cannot be greater than 1, nor can it be less than 0. Okay. Probability values are always between 0 and 1. Questions? Okay. And now we'll look at conditional probability, another type of probability. Now in this case, here's the definition. We let A and B be two events. The probability that B will occur given that A has already occurred is called the conditional probability of B. And it's denoted by this notation right here, where we got the P on the outside and then B with a vertical bar. And then A, that's the probability of B given A, or the probability of event B given that event A has already happened. Okay. So let's say we have a bag containing 3 blue marbles, 2 green marbles, 1 yellow marble. And here's the experiment consisting of drawing 2 marbles from the bag, one at a time without replacement. Okay, and what that means is we don't replace the first marble after it is drawn. And I want the probability, or we want the probability of that given that the second marble is green, given that the first marble is blue, and then part B, the second marble is green, given that the first marble is green. Okay, here's how they compute those probabilities. So here the first marble is blue. That means that 5 marbles remain. 2 blue marbles, 2 green marbles, and 1 yellow marble. Okay. So that probability that the second marble is green will be 2/5. So the probability of getting a green marble given that the blue marble was drawn would be 2/5. Okay. Questions on how they got that? Okay. Because that first marble we drew was blue. That means that there are 5 remaining. Because we started off with 3 blue marbles, now we have 2. And then you got 2 green marbles and 1 yellow marble. Okay. And I might be better to show this up here. Okay. 3 blue marbles. I'm gonna let these circles be the blue marbles. The 2 green marbles. And since I don't have a yellow marker, I use orange. I'll let that be yellow. So we know we were given a blue, the first marble was blue. That's taken out. So now we got these 5 marbles remaining. 2 blue, 2 green, and 1 yellow. So that means the probability of a green given the blue marble, there are 2 green marbles out of the remaining 5. So that's why that probability is 2/5. Okay. All right, now for the part B, where we're finding the probability that finding the second marble that's green, given that the first marble is also green. Okay. All right, so we know the first marble is green. That means that there are going to be 5 marbles remaining. All right, so if I circle one of these green marbles, which is given, that means that there are 5 marbles remaining. In this case, 3 blue, 1 green, 1 yellow. So this time, the probability of selecting a green marble on the second pool, given that the first one is green, I only got 1 left. So that's 1/5. Okay. First marble that we know is that we pulled out was green. The probability of getting a green on the second draw, there's only 1 left, so it'll be 1 out of 5. Any questions on this? It's just a visual representation of those 2 examples here. Okay. Let's talk about this particular example, E, F, and G, which is the rest of problem number 5. Okay. So here we got that same Venn diagram. With 15 dots, okay? Equally likely outcomes. Each one has an equal chance of being selected. Okay. So here we want the probability that event A will occur given that event B has occurred. So that's the notation that we write for this. Probability of event A given that B has occurred. Okay. Now we're given that this event B has occurred. And in this case, let's look at event B. How many dots do we have here? There's 10. The 10 goes in the denominator. And we want the probability of event A occurring, given that B has already happened. Well, let's look at this. This intersection of A and B. How many dots are there? 3. That's going to be the answer right there. Because notice, these 3 dots are also in A, and there are 10 dots in B. So it'd be 3/10. Question? Okay, I thought. Okay. So 3/10 as a percent is 30%. So probability that event A, given that event B has occurred, would be 3/10.
We may have some questions. Why are we pulling the 10? Is that for
Because event B has already occurred. So we're looking at just event B right here.
Okay, so in my head, it's the opposite. In my head, if B has occurred, I'm trying to ignore it. I'm looking at only A, but that's not the case.
Right.
So does it matter if you don't go after they or not?
Oh, it does matter. Because if these didn't overlap, then that wouldn't happen. Mhm. Any other questions? All right, now part F. The probability that event B will occur given that A has already happened. So this is B given A. B goes first and then A after that. So let's look at event A first. A has already happened. This is event A. How many dots are there in event A? Six. But what's the number of dots that are in the intersection of A and B? It's 3. So it'll be 3/6. And that's a percent. This will be 50%. Okay. Now let's look at part G, where it says it was the probability that event B will occur, given that event A did not occur. So let's say A did not occur. Here's event A. Now, the opposite of that, we just cover up A. Yeah, it'd be 9, because we got these 7 dots in B and these 2 on the outside. That 9 would be in the denominator. Now, out of those 9 dots, how many are in event B? 7. So this will be 7 out of 9. Okay. Questions about E, F, and G? Okay. And with that, I will stop right here. And I will pick up with the rest of section 9.2. Okay. So the rest of section 9.2 I will cover on Wednesday. And, yeah, 9.2. All right. And don't forget about the out of class assignment that's due Wednesday. Exam number 2 is due on Saturday evening.
Ask you about the out of class assignment. But, I mean,